Hello, and welcome to this special demo for EET 3229C Communication Systems at Valencia College for the fall semester of 2020. And this is your lecturer, Dr. Wilfredo Rivas Torres. And on this special demonstration, I will be talking about the eye diagram and modulation constellation. Um, and essentially, there's no slides. It'll all be demos using Octave. So why don't we go ahead and get started? So for this demonstration, I'm actually going to use two scripts. Um, One of them is based on a script that's at the end of chapter 6, and it has to do with the uh, eye diagram of certain PAM, pulse amplitude modulated signals. I did add a raised cosine filter pulse shape to that and a few other little things to help with this demonstration. And we'll be looking at that. The second script is actually lab 3 of the course that I'll use for some demonstration because we need MARI, different modulation types to be able to look at the constellation because we need to have complex signals, right? And complex, I'm talking in the sense of real and imaginary portions or I and Q. Um, and for that, I'm going to need a different kind of modulations, and we'll get into that. But first, let's go and run our pulse amplitude modulation. Hopefully, you guys can see the text from the video. So I have a signal to noise ratio variable. We'll come back to that in a second. Um, uh, the one thing is we normally test our digital communication system with a bit stream. Now you have to come up with a bit stream, right? You would normally, in the real case, have either some audio, some video, or some movie that includes both audio and video uh, that you have digitized, whatever other source of information, sensors out in the field, all this stuff is digitized. So we're going to normally start our analysis from having a bit stream. And normally we do all our analysis and simulations with a random set of bits. So we have to have a way of creating random bits. So that's why we use this rand_n function, right? So we're going to create n random uh, samples. And I know the comment here says 400, but I meant to make it 100. So we're going to create 100 random bits. So this random function creates a number between 0 and 1, if memory serves me right. And what this sign function does, it'll actually, random n produces random numbers, and I forget exactly why they call it n. But it has to be able to produce positive and negative numbers because we use the sign function to then make it either a +1 if it's positive number and -1 if it's a negative number. Um, the next thing that we're going to do is we establish a sampling factor. We've been doing this throughout the whole course, so something not new to you guys. Um, then the other thing is this is a new function. We're going to upsample it. So data only produces, right? It's going to be 1 and -1 for our binary data. But we need to upsample it. We need more than just one sample per bit, okay? If you think about it, right? Because that's what our data again is binary data, which we call them bits, right? So we create our data and we want to create it, upsample it, and we're going to just go ahead and upsample it by a factor of 100, okay? That's what this tau is telling us, right? The rest of the things is we're creating the different the different pulse shapes that we want. So this YRC, which stands for our signal return to 0, right? And it's going to be polar because it's going to have positive and negative numbers, positive plus or -1 actually. And the way we sort of shape our signal here is we take the upconverted, and I know it says convolution, and some of you might say, oh, convolution is used for something very particular and LTI system, and that is correct. But it also, you can use it, and this is a trick that we normally use a lot, we use it for pulse shaping. It can also do that, because if you think about it, what you have is a series of samples, right? In our case, every bit is going to have 100 samples, and we want to pulse shape that bit, right, over the 100 samples. That's what this is doing. This is what that convolution is doing. And we're using this PRC function, right? Again, that's a function from the end of chapter 6, which stands for a return to zero polar signal. Um, and then we just pick out a series of samples from there that we want to look at, right? Um, we will add noise to it. Now, um, I want to reserve this comment about noise for a little bit later, when we start experimenting with the signal to noise ratio, okay? So we also are going to create a non-return zero. We have another pulse called PNRZ, right? And we're just going to create the same thing with our same upsample data. And we're going to do a convolution with PNRZ to create the non-return to zero data. And we're going to look at, don't worry if you're struggling a little bit to see what other different pulses are. When we run the script, you're going to see all these waveforms in the time domain, and I'll go through this again. Again, skipping the noise addition. Then we're going to have a sine pulse. We never saw that in the course, but we saw at the end in chapter 6 example, and I think it's a good example. It's something good to look at because we're sort of familiar with this sine function. So it's just a positive. Take the sinusoidal a sine waveform, right? Starts at 0, goes up to 1, comes down, and then you will see the negatives. It's only the half sign, so it's only the positive sign. And then we plus and minus that. When you see the waveform, it'll hopefully become logical to you guys, right? And then again, we do the whole convolution thing. And then I do a raised cosine filter, right? That's the filter that we use to reduce inner symbol interference, right? We're also going to do that pulse shape before you guys, so you guys can get a sense of what that looks like when applied to a binary signal. And again, we do the same thing. We do the convolution, this time with a property, right, with an impulse response of a raised cosine filter, which is what you guys are more used to. And then that's about it. After this, it's just plotting the signal and that we're interested in. Um, there is some iPlots functions that run here, but let's run it and first look at the time domain waveform, so the pulses, right? So conveniently, I already ran it before I started the video recording, right? So here's what they look like. Let me expand a little bit. Hopefully you guys can see it a little bit better. And I'm just looking at the first 10 seconds. It runs more data than that. But if you put so much data, you really can't see what's going on the plot. Okay, so from the top plot, you can kind of see what the return 0 does. So hopefully you guys can see my marker. And we'll run it one more time so we get to see this again. And so you guys can see the random bits nature of this. So the first bit starts at 0, because remember, it's returned to 0, so it starts at 0. We have a -1 that indicates we have a binary 0. Goes back to 0. Then at 1 second is where the other bit starts, because I neglected to tell you in the script that I made the bit time 1 second. Then here's another bit, and then it produces a series of 4 zeros, 1, 2, 3, 4 zeros, right? And then on the 4th second, it produces, or 4th second time interval, it produces a +1. This is a 1, right? And the -1s are the zeros. So 1 and a 1 and a 0 and a 0 and a 1 and a 1. All right. So how does that look in non-return 0? Well, in non-return zeros, the zeros are -1, so you have a 0, another 0, 0. But remember, they all last 1 second. 0, then the two ones, then the two zeros, and then two ones. Okay. Now here's that half sine waveform. So again, because it's a 0, you get a sine wave that sort of goes down, and then another one, and another one, another one. Then when you have the two ones, then it goes in the positive direction, and you build up a signal that looks sort of like this, right? Um, Actually, it looks like that a PSK signal if you really go back and think about it, right? It kind of looks like a PSK signal where you're interrupting the phase, but that's not really what's happening in this simple example. Um, the root cosine filter is a little bit trickier to catch and see where the ones and the zeros are. But because we have it right below the non-return zero, we kind of can see what happens, right? Notice that when it starts off at around zero point 0.5, and you're wondering where this zero point 0.5 comes from. It it's just part of the Roig's cosine filter. Okay, let's not dwell too much on that. But if you look at where we would sample it, remember that we always say that when we're doing the bits, there's always a we call it the time uh, the bit decision point time, right, or the decision instance. That's what this is, right? Notice it crosses -1 right there. That's where probably where you would have that decision, and that's here's the other decision. What happens to coincide with the center of the bit, right? The same thing in one, maybe it's a little bit easier to see. Here's where that one would cross, and this is where you would be taking your decision, and this is where you'll be doing your other decision, right? Don't be fooled because it kind of looks sinusoidal. That's why I want to run it again. So let's go ahead and run the script, right? So here's the script. I'm just going to go ahead and run the script, and we want to ignore this for now. Let me put it out of the way. So now we have a different set of bits, right? Hopefully now it doesn't look so sinusoidal when you look at the raised cosine filter, and you can see you have different bits. And this is a good thing for you to do, right? You want to see random bits and run it several times to sort of get a feel for what your system is doing, what the raised cosine filter looks like, then the different signals. And we should even go ahead and run it a third time for, I'm looking for one that produces lots of ones, but oh, there you go. There's one that produces lots of ones. Okay, so just to show you guys that it's truly random, right? Um, and it so happens if you have 1 0 1 0 that the half sine wave actually looks, guess what, like a sine wave, right? And kind of you can see what happens with the non-return 0 1 0 1 0 and the root cosine shape, right? Notice that of all of these pulse shapes, the raised cosine waveform actually exceeds ±1. But that's okay. Remember, we only are interested in that the ideal decision point, right? When we have to make that decision, is it a 1 or a 0, right? When we're working for digital um, um, signals, that's what we care about the most. Now, this ideal decision time, right? You might hear people calling it bit slicing and sort of that sort of terminology. It's the same thing, right? What you're doing is you're trying to make a decision. Do I have a 1 or a 0? Okay. Now let's go back to the code real quick because I skipped over a few things. One of those was the eye diagrams of which we're plotting. Now I do have a function called iPlot. It's a special function. This is the one that the book wrote at the end. I believe that Octave comes with an iPlot function, same as MATLAB, but in MATLAB you need a communication toolbox. Being that with Octave we have many of the toolboxes, you can use the iPlot from Octave, but I just follow our textbook author's lead and I use their same iPlot function, okay? Um, and it takes simple parameters. By the way, you do have this function because it's part of Lab 3. Um, so you tell it what is the data. Uh, the next parameter is the width of the eye plot. So if you remember from the lecture, I said sometimes you just plot one eye, and sometimes we like to plot two or two cycles, right? So we are normally people plot two cycles. So this n width, if you look closely here, it's two. You always tell your eye diagram what your sampling rate is, right? And then there is always a delay. Eye diagrams always have a delay. And you can use this delay in several ways, right? If you make the delay here, this one example says 0, you'll notice I have a 1 over tau over here and 2 over tau for the raised cosine. Normally, this is also the place for the eye diagram where you get rid of the transients, right? So if it goes through a filter, you have a transient, you really don't want to look at the transient, this is where you get rid of it. Also, it looks like sometimes this function, when it processes the eye, it sort of shifts everything by one or two samples depending on exactly the way the convolution ended up. So I also actually compensated for that so that everything lines up. And that is not uncommon. That's fairly common when you're doing eye diagram simulations, right? The instrumentation, right? There's instruments that come with eye diagrams. The digital people do this all the time, right? So especially when they do something called signal integrity, right? They're trying to make sure that and they use one of their tools is still eye diagrams. Um, Even though their channels are very different than the ones that we're talking about, but it's still a channel, right? So it still has sort of this low pass kind of frequency response. Um, so where I was going. So the instruments know how to align the symbols, and they have sophisticated software to do that. We are obviously not trying to do any of that here. So our iPlot function is fairly simple, and you guys can look at the code and kind of get an idea of how that works. But remember that what the eye diagram is doing is something that's simple that you can do with an oscilloscope. You pick one or two cycles and you just put the same data on top of each other. You don't erase the data, you just accumulate this data. Okay. Now, I'm going to go back to the time domain just so you guys remember it, right? And I'm going to bring in the eye diagram slowly. Okay. So here's the non-return zero the return zero waveform, sorry. And this is the return zero eye diagram, right? They're both on the top left-hand side. Now, if you look at this signal, right, the return signal, it starts at 0, goes 0 for like a quarter of the time. Notice, quarter of the time it stays at 0. Then, in this case, it goes down, then goes back up. So it goes down, and then it would, in theory, go up. And because we're only interested in two cycles, for the next 2 bits, so from 2 to 4 now, we would again go down, and they're overlaying each other on this eye diagram. It's just that our signals right now are perfect. There's no distortion, there's no low pass filtering, there's nothing. This is just perfect digital waveforms, right? And then at some point, you're going to see, like when you go from 4 to 6, oh, this time they both stay positive. So the signal goes up, comes in, goes up, down, crosses over, and then up. And then you can start seeing how you start getting your two eye diagrams for the return zero. The same, I can follow the same logic and show you guys how this half sine wave works, right? So the first 2 seconds create, first it goes down, then goes up, and eventually when you retrace it, you'll see you start making these sort of eye plots, right? We call them the eye diagram. Let's cross over to the non-return zero, right? So let me go do that. So the return zero is kind of interesting. Ideally it goes from -1 to 1, and it does that in 0 time. In the real world, that doesn't really happen. There's always a rise and a fall time. The same thing with the return 0, by the way. But here you can see it goes straight up, right? And so the eye diagram kind of reflects that, right? It goes almost straight up. But the only reason that's a little bit of an illusion. Right now, our sampling rate is, oh, gotta go back to the code, I forgot. What the value of sampling rate, that's our value, the tau, it's 100, right? So when you look at 100 and we try to look at this, right? What happens is every 1 second you have 100 points. So it's really hard to distinguish where it is that it goes from 0 to 1, but there is a 100th of a second difference. And it looks fairly vertical, doesn't it? The same thing happens in the eye diagram, but the eye diagram, you can almost see it, right? So why don't we play a little bit? Let's say instead of 100, we go to 50, right? Let's see if we see a little bit of that. Let's look at the waveforms first. Now, this is something that you guys will also notice. When you're doing these simulations and depending on your sample rate, etc., you will see that the simulations sometimes take a little bit longer, etc. Okay, so you'll notice that even with 50, you still can't see it. There is a little bit of a rise time, but it's just hard to see. Okay, and there's something in my code that it didn't like when I went to 50. Oh, okay. Sorry, so it just doesn't like 50 for the sampling rate because I didn't select all my vectors to have the right length, and some of them did not like that. All right, so let's stick with the 100 for now. Okay, so let's go back to that. All right, so here's what I'm saying, right? I'm waiting. There's the eye diagram. So it took a little longer. Okay. And again, the higher sampling rates, and if you set all your vectors to follow it appropriately, it will do that. An interesting eye diagram is the one for the raised cosine waveform. You'll see that all of a sudden it doesn't follow the really nice, shape that the other ones did. And here you can actually see where we're overlaying all the different traces, right? What happens is depending on the bit stream, these rise and falls will be different. And you can definitely see it here. But if you remember, right, when we talked in class, here's that optimum decision point, right, at 0.5 and 1.5, which is where we want them, right? You can see that they all coincide to the same point, okay? So, and we said in the lecture that that's what we want because that reduces our inner symbol interference, right? And that's the whole purpose of using these raised cosine filters, okay? And that's what it means. It means that at the exact decision point, we will have the best sampling instance. Now, a couple of things, eye-opening. So in the other ones, it's kind of obvious that the eyes are wide open, right? There's nothing that interferes inside this region, right? Now, the return 0 one seems to have a narrower eye region compared to the non-return 0 one, but it's considered wide open, right? Even this half sine wave, even though it's not squarish, it doesn't have the same quote unquote area, but it's considered completely open. Now, the raised cosine filter, not necessarily, right? Because if I compare it to the sine diagram, you can see the eye is definitely not as open. However, it's maximally open at the uh, optimized sampling instant, right? So at the sampling instant, you have uh, maximum wide opening. Okay. All right. So now let's go back to the code. I said we weren't doing anything with noise, and it's going to surprise you guys. Hopefully by now, I set the signal to noise ratio to 50 dB. That's a really large number, right? So our noise is really small compared to our signal, right? Now the way we're going to add noise, we're going to use this AWGN function that stands for additive white Gaussian noise, which is in essence for everything we know, that's our channel in this case, okay? And it's a function. It comes with Octave and MATLAB, and that's its function. It's what it does. It adds noise to our signal based on the signal to noise ratio. Okay, so you feed it a signal, the YNRC or the YRC, the YR cos, whatever the signal is, and you tell it the signal to noise ratio, and it will add random noise to your signal. Right? So why don't we start reducing the signal to noise ratio and see what happens, right? So I'm going to go in steps of 10 and we'll kind of talk through it a little bit. Okay, so let's go down to 40, right? So looking at the signal, oh, sorry, I need to wait till the whole thing finishes. There we go. All right, so if you look closely at the signals, now that I went from 50 to 40, you start seeing that the signal has these little ripples that were not there before. Anytime you see a signal that doesn't look like the ideal signal, some kind of interference, distortion, or noise got into your signal. In this case, it is noise, right? Which is a form of distortion, right? But it's random, and you can see little interferences, and then a little changes in the signal, I should say. And then here are the eye diagrams, right? And again, you can sort of see them um, as they also affect the eye diagrams. I wouldn't say that the eyes are beginning to close. There's a little bit of eye closure, but it's hard to tell, right? And if this were an instrumentation, we wouldn't even be talking about it, okay, in the real world. So let's go to 30. And again, I have to learn to be patient a little bit, okay? There you go. There's our eye diagrams. Now you can, when you look at the signal, the noise is completely apparent to us where that noise is happening, right? I could have looked at this, or I could have looked at the eye diagrams, right? And you can definitely see now the distance, the vertical distance at the sampling in uh, point, right? At point 0.5 and 1.5, you begin to see that this overall vertical distance is less, right? And then we can do a few more numbers. I promised to go down in steps of 10, so let's go to 20, right? And again, learn to be patient. There we go. So definitely our signals are becoming more and more distorted by the noise, right? So that once the signal goes through the channel, it picks up a significant amount of noise. And you can see now the eye diagrams are really beginning to close, right? You can almost see, right? You're beginning to lose like, oh, I want to say half of the one of these um, uh, vertical minor distances, which is about zero point 0.1 or so and zero point 0.1 or so. So now the eye is only zero point 0.8. Almost all of them are about the same. They closed about zero point 0.8, right? So instead of being plus or minus 1 at the sampling instance, they're a little bit less, right? Um, then if we keep coming down, let's say to 10, right? Uh, Again, a little bit of patience here, all right? Now you see the signals are really have a lot of noise. Sometimes you can see the noise really peaks beyond what it should have been, right? This is a return to zero. Notice that it hardly spends any time at zero now. The same thing with the return zeros. You can see that actually here's a sample that crossed the limit, right? Our decision limit is the vertical zero line, the horizontal, I should say, zero line. And you can see you cross it a couple of times. So if you try to sample here, you're really into trouble, right? And then the eyes, well, the poor things, they're getting really shut, right? You really just cannot see what's going on. And the raised cosine filter, you can almost see that the eyes are totally closed this first half. And even the second half is beginning to be almost totally closed. You can see some of these peaks are really bad. On the return zero one, that also, a lot of them seem to be in the, even on the non-return zero one. So a lot of them are beginning to cross the boundary. If I go to 0, it's obviously, the noise and the signal are the same. So that should not be a surprise that that's not a good situation in most cases. It's not in all cases, right? But for what we know, for the purpose of our class, they are. I'm going to just show you guys 5, right? Again, being a little bit patient here. Again, you can see now that the noise is really hard to even recognize what the original signals are, and there's so much noise. And obviously, I should fix a little bit the vertical axes here so that we can see more how far the noise is going. But you can see now that you're really crossing the boundary a lot, right? That 0 boundary, right? And the eyes are pretty much, they all collapsed, right? There's nothing we can do here. And here's a case where you have so much noise that you're probably going to have a lot of bit error rate, right? So meaning you sample, and instead of having you send a 1 and you get a 0, or you send a 0 and you get a 1, and that will count as an error. And with such a low bit error rate, you probably such a low signal to noise ratio, you'll probably get a high bit error rate. Okay, so, and we also know that the channel capacity and signal to noise ratio are also related to each other, right? If you guys remember Shannon's law. All right, so 20 is kind of looks like a reasonable thing, right? Uh, Lots of practitioners will say 10 or 20 signal to noise ratio, and they kind of use that as a measuring stick. It's not what we call a rule of thumb. It's just kind of, hey, if you can get somewhere between 10 and 20, you feel confident you can make things work. Are there systems that work with less than that? Oh, absolutely. There's a lot more digital techniques that we just haven't discussed in this course, and just did not. It's just not the purpose of the course. Again, it was a introductory communications course. All right. So I think we experimented quite a bit with the eye diagram. Hopefully, this helps you, especially if you see this before laboratory number 3. It'll help a lot that you guys answer the questions in the lab. All right, let me go then move on to the other script, the one that you guys are actually going to be using in the lab. Let me reset this. I believe I started that with 50, so I save it with that for future generations. All right. So I'm not going to go too in deep in the details of uh, the script for the lab, because I do describe it in quite detail in the pre-lab work. Um, but suffice to say that we are going to pulse shape with a raised cosine filter. We're going to generate different modulations, MRE modulations, BPSK, QPSK, all the way to 16 QPSK and even 16 QAM. We do have a signal to noise ratio, and this time we do have the number of symbols. So we're going to send a series of symbols through this channel, okay? And that's, again, when you guys read the lab, you'll understand a little bit more. So um, if you haven't read the lab, I strongly suggest you stop now, go read the pre-work portion of the lab, and then come back and see this part of the video. Or you might want to see this video, go read the pre-lab, and then come see the video one more time. Okay, those are kind of my recommendations for you and for lab number 3. Now, the way this is going to work is you always have to put in here the modulation that you're interested in studying. Right now it's set for QPSK. We can start with BPSK if you guys want, but I'm going to hang on to that. And the number of symbols. So when you're studying bit error rate, I will say this: how many symbols you actually, how many bits you send through the system is an important factor, right? So let's say you want to measure 1 e to the minus 3 bit error rate, right? When one e to the minus 3, or same as 10 to the minus 3, means is you're going to get 1 error every 1,000 bits. You're allowed that. That's your specification for your system. And that's, in the old times, that might have been a good thing, and in modern times, that's fairly lousy. Um, But let's say that, right? 1 e to the minus 3 is the bit error rate that you can tolerate. Now, that means only one error in 1,000 bits. Now, in order to do a good measure of bit error rate, you have to have a good statistical sample, right? That means you need more than one, right? So normally, right, and depending on who you talk to, who's the practitioner, people will say, well, maybe the least amount that you really want to see, you want to see somewhere around 30 uh, errors or bits that are wrong, right? To get a good sense of how your system works. Others will tell you 100, and others will tell you as many as you can get, right? So if that's the case, right, instead of 1,000, and I want to run, let's say, the minimum of 30, that means I need to run 30,000 bits before I can say I have a good measure of what my bit error rate is. And again, guys, the problem is way more complicated than that, how people make these decisions, but again, beyond what this course, you want to cover in this course. So now you can see instead of 1,000 bits, you really don't run 1,000 bits, you have to run 30,000, right? So we do study that a little bit in the lab, right? So I do have you guys change these numbers. But for now, I'm going to stick to 10,000 because this is just a demonstration and I don't want to give too much of the lab away. And we're going to start with QPSK. Um, and I want to run things in a reasonable amount of time. The bigger you make this number, the longer the simulation will take. So please learn to be patient. All right, so let's go ahead and run this one. I believe I closed the other two figures so that sometimes Octave doesn't really like that. Okay, it did. I did close them. So here we go. Notice that I do have a little status window for you. One says running and the other one says done. So when you have more bits, the running window, which is the status window, stays up a little bit longer, letting you know the simulation is still running. So don't cover that little window so that you can see it. Okay, here's the results from running that, right? Oh, by the way, notice the signal to noise ratio is 50, so I start off with very little noise. And I create noise the same way I did for the eye diagram demonstration. Okay, so here's the results. I plot a few things for you guys. I'm really interested in the lab in the top left-hand side and the bottom right-hand side. So in the constellation and the eye diagram. The other two are there for your reference. Um, so we start off on the top right. Here's the constellation. Now, let me see if I can turn off the green dots. Let me see if I remember how to do that. I want to turn that off real quick. It's the second. It's the first one actually. And this is constellation. Yeah, this is the one I want to try to turn on. Hopefully it will not. There's the running status is running. Done. No, I turned off the wrong one. I left the green ones on. Um, really? Yep, I did. I meant to turn off because that's because I wasn't paying attention. These are the red ones. Where is the one for the green? Oh, it's the couple of lines above that one. That's the green one. Okay. All right. All right. It still didn't turn them off. Why not? Oh, because I didn't clear. I should clear it first. Okay. All right. Let me just make sure that I cleared it. Yep, the figure is totally cleared now. All right. Let's go ahead and run that. Sorry for a little bit back and forth. Okay. But this is what I wanted to show. All right. So hopefully you guys can see the red crosses now, right? With all the green stuff around it. These are what we call this is the ideal constellation. No noise, no distortion, no nothing. This is where the constellation should always be. What you'll notice is when you add distortion, be it whatever form it is, noise, these dots will spread around these points, right? The more they spread, the more noise or interference or distortion you have, okay? Kind of similar to what we did with the eye diagram, right? So here's the QPSK before any pulse shaping. That's the top right-hand side. So that's the eye diagram. It's pretty much for the pulse amplitude waveform right before we modulate it. Okay. Um, so that's all ideal. That's in the transmitter. Now, on the bottom here is what you would see on the receiver side. Okay. So on the receiver side, this is the spectrum or power spectral density of the waveform. Now, in our case, I make the symbol rate always the same, doesn't matter the simulation, right? But one of the effects of that is that the bandwidth, the spectrum of the signal does not really change, and the bandwidth does not change much. You might see some level changes, and they're not that easy to see because they're just like 3 or 6 dBs, and on this scale, they're not always apparent to you. But it's there for you because I want you guys to see the shape, and I guys want you guys to see that. Instead of changing, of keeping the symbol rate constant, I had kept the bit rate constant, then you would have seen this bandwidth change. Okay, um, that was just my preference. In the real world, depends on what you're doing, right? Again, if you change the bit rate, it should change. If you change this, if you keep the, if you keep the bit rate constant, this spectrum will change. But if you keep the symbol rate constant, then this will not change. And you guys should know what's the difference between a bit and a symbol, right? Remember, a symbol, a single bit is a symbol, it's a 1 bit symbol. But then when you group bits together, right, you create other symbols, and that's where you get your pulse amplitude modulation with different M-ary levels. Okay. And then this is the QPSK signal eye diagram. Okay. Um, Not surprising, right? Because it looks like that return zero signal. If you look at the eye diagram for the QPSK, it looks just like it, right? The ideal eye diagram looks like the ideal non return zero one. So does the eye diagram for QPSK looks like the return zero. Okay. Because the digital data so happens, and that's what it is. But remember, QPSK is a complex signal, so we're only looking at the in phase, right? We could have looked at both the in phase and quadrature phase, and some people do that. It doesn't necessarily give you that much more information unless your system has a problem with either in phase or quadrature phase. But most systems, whatever interferes with one interferes with the other one. Okay, and you guys can kind of have an idea what in phase and quadrature phase mean. Okay, so let me go back and turn on now the green dots. The green dots are actually the ones that are received. So again, the red ones, the red dots, not only serve as our reference, are actually when you create the waveform for this eye diagram, right? Or ideal diagram, this is where uh, the points would land on the constellation. And you can think about the x as being the real axis and the y being the imaginary axis, or x is the in phase and y is the quadrature phase, however you wish to look at it. Now, when we turn on the green ones, now the green ones are circles that, in the ideal case, with this really high signal to noise ratio, they just land on top of the crosses, right? And again, everything is ideal right now, so I'm really not adding noise to the channel. But let's go do that, okay? So we know that around 20, right, is when we start to see some of the noise, or we felt comfortable that that's where there's noise. Let's go to 20. Let's see what happens, right? Again, status window, done. Okay, there's everybody. All right. Now you can see why I keep the red crosses on there, right? You can see that now all the green dots are beginning to spread out. Again, I don't expect changes in the ideal diagram nor in the frequency spectrum. Just I don't expect, there's no reason for those two to change. So the power spectral density will have small changes here and there. It's hardly noticeable. But you can see now in the eye diagrams, all the bits, all the symbols are beginning to sort of spread out from where the ideal one would be, or your reference constellation points would be, right? You're getting spreading, um, and that is correct, right? That's what the noise does. So now when you go to that ideal sampling point, what that means is they don't all land on the same place. And in fact, if you look at this eye diagram, right? The ideal sampling point is still zero point 0.5 and 1.5. You can see how that eye closure in this case is beginning to happen, right? You no longer have the eye as open as it was a little while ago, okay? It doesn't look noisy anymore, right? And there's several reasons for that. And filtering has a lot to do with it, okay? The way we're doing filtering, but you guys don't need to know that detail. But you can see how the spreading is happening at the ideal sampling time, right? All right, and if I reduce it to 10, um, I will, I need to say something that I've been sort of skipping over. In the top left-hand plot, I do put something else other than calling it the constellation and telling you what the signal to noise ratio is. I also tell you what the bit error rate is. Then this is the bit error rate that was measured. Now you guys are going to measure the bit error rate in the lab. It's going to be a little bit different. So right now these numbers are not something that we're going to pay attention to. Okay, this for this demonstration, but you guys in the lab will be doing that. Okay, um, and just pay careful attention to the instructions in the lab. Okay, all right. So let's go ahead and do another signal to noise ratio. Let's reduce it to 10. All right, let's go ahead and run that one. All right. And as you know, I reduce the signal to noise ratio. And if I reduce the signal to noise ratio, that means that the signal is going to experience more distortion or more noise, however you want to say it. And you can see how all the points now begin to spread out more, right? And it's getting almost difficult to tell which point belongs to which part of the constellation. Actually, there's this one green point here that is about equal distance from this one in the upper right hand quadrant to the lower right hand quadrant. See, this point is halfway through. So what does it belong to this guy, right? To the top one or to the bottom one in this case, right? And you start seeing that in the x direction that can also happen, right? Notice how the eye diagram now is beginning to close, right? I can actually reduce the signal to noise ratio to about 5, right? And if I reduce it to about 5, now you can see that the points really go back and forth. And notice that bit error rate had been 0 all this time, and all of a sudden I'm beginning to have some bit error rate. Okay? Again, you guys are going to start answering that in the lab uh, and looking at that. Again, the eye closure is worse than before. And actually, the spectrum, you can start seeing some of the noise, right? Some of the noise out here. Again, because this is on the receive side, and there's a really nice filtering, even that's not really an issue, right? As we see it, right? But it is an issue that you can noticeably see both in the constellation diagram and in the eye diagram, okay? Now, a quick note about the lab. Let me bring up this. spreadsheet. This is something, spreadsheet that is part of the lab. So my demo is done. I'm not going to do any more on the demo, but I will mention this. You guys just saw me change signal to noise ratio, and I want you guys to fill this in for the lab, right? Actually, I want to go back to the demo and just to do a few more different kinds of modulation. So we did we did a few of these in QPSK. Oh, I'm just going to punch in some random numbers, 1 e to the minus 3. You see the graph begins to update, and if you are putting in the right data, right? Something like, let me make this 1 e to the minus 4 or so. Oh, right? And I didn't mean to the minus 4, I meant to the minus 2, right? So something like this is going to begin to happen, right? So the graph is going to begin to update as you put more data in it. And we can put data over here. Oops, because they sort of fell on top of each other. 1 e to the minus 4. Um, I can say this is 0.05, so just so they don't fall on top of each other and you guys can kind of see them. Um, 0.03, etc. Let's say that that's the right data, okay? Couple of things. Let me, maybe you guys can't even see the numbers. Uh, Zoom in a little bit. So see, you're going to begin filling in. By default, everything is 1 e to the minus 6, right? When everything is 1 e to the minus 6, like I had a little while ago, right? The graph appears to be blank. So in the lab, whenever you run it and your bit error rate comes out to 0, and remember where you're going to get your bit error rate information from, right here, okay, from this top left curve, that's the number that you're going to fill into the spreadsheet. Now, if you do get 0, do not change the 1 e to the minus 6, because if I put 0, that's what you're going to get, right? It's going to tell you, oh, I can't do it. And the reason for that is because this y-axis is what we call a log scale. And the reason I did it as a log scale is so that it looks like it normally looks in the textbooks, right? If you're thinking, oh, I've never used a log scale before, I don't even know what that is. Well, I have news for you guys. We've been using it in the course all along. That's why we do things in DB, right? DB actually is a way of putting things in a certain log scale, right? And that's kind of what this is doing, but most of the time people don't talk about BER and DB. We just talk about it in ratios, right? And that's what this is, okay? And that's about what I wanted to say. I want to make sure you guys fill in this data correctly. And if you fill it in correctly, you'll see a series of graphs that you might be able to recognize from some of the lectures. Okay. All right. The one thing that I still owe you guys is more of these modulations, right? So let's go to 20. Let's say what does BPSK look like, right? BPSK stands for binary phase shift keying, right? It's just binary, so it only has two symbols. So we should be able to just see the two symbols. All right, and this is what the two symbols look like, and this is the ideal eye diagram. Again, it looks like that returns 0, 1, doesn't it? And the eye diagram too. Yeah, quite interesting, right? All right, so if when I want to do 8 PSK, I can come here, 8 PSK. You have to type it exactly. I do apologize. If you make a mistake, it will be unkind to you, and it will just, right? Let's say I put 7 PSK, which is not really an option. It tells you invalid modulation type. Okay, so if you see the invalid modulation type, oops, you made a mistake. Just come back here and make sure you type in the right, uh, type it right. And in this case, sensitive, so everything has to be capital letters. Okay, so when I run the APSK, right, you got a little patience. You get a constellation of 8 numbers, and they're all with the same magnitude, if you will, right? Like they all fall on the unitary circle. Notice the eye diagram. This is the first one where you have a multi-level eye diagram. So there's 3 levels. There's 1, 2, and 3. That's the ideal eye diagram. Now you see why I put the ideal diagram here, so you can see how much from each modulation. And then you can see the one for received, which has the raised cosine filter. And again, you should see three distinct eyes in the vertical, right? And you do still see those. Okay. 16 PSK is quite interesting in the sense you'll see the eye diagram, see why I call it quite interesting. So that one, right? It's really hard to see. Actually, why don't we go ahead and get rid of all the noise? Let's go back to 50. Signal to noise ratio. Um, Let everything update. Okay. So now you can see you have the 16 points. Again, they're all in a unitary circle. They all have magnitude of 1 and a certain increment and the phase, something we discussed in the lecture. It's just that look at the eye diagram, right? You have 1, 2, 3, 4, 5, 6, 7 eyes. The problem is they're not all the same height. Isn't that interesting? Makes for an interesting sampling uh, situation. I'm not going to call it a problem. Okay. And then you can see what the ideal sampling periods are. Okay. 16 PSK is quite interesting because we just haven't seen that before, right? Different levels and different stuff. Um, okay. And that's because of the face that I'm using. I can actually go, I don't want you guys doing this in the lab, but I can actually go in here and change this to, I'm going to just multiply by 0. And you can see that, you're going to see that 16 PSK, right? It's going to look different. Now you can see the difference between the top and the bottom are really, really small, right? So now you know why phase, that initial phase uh, does play a role in here, right? Initially, the eye was going to be fairly close. No, oops, I didn't mean to click on that. Uh, when I rotate it a little bit, give it a little bit of an initial phase, this eye is a little bit wider, right? And people can and you can sort of play with it a little bit, see if you can find a better a wider opening. If you want to experiment for yourself, it's not part of the lab, but it's just an idea of things that you guys can try. Okay. All right. Oh, the last one, the one that I'm still missing is the 16 QAM, right? QAM stands for quadrature amplitude modulation. We do have that one. Oops. Right. If I run it like that, I should see an error, and sure enough, right? Why did I get an error? Because even though everything is capital, I wrote AQM and it's QAM, QAM. Okay. Um, And this is 16 QAM, right? You can see everything is on a fixed grid now. Isn't that kind of nice? Or it kind of looks nice. All the eyes have, again, you have three double eye, but they're all the same height, which is a good thing for us, right? Or we think it's a good thing. Um, and then you can clearly see what the raised cosine filter does to the eye. And again, you have three eyes vertically, and you can see them wide open right now. Okay. And again, we can put a little bit of noise on there so that you kind of see what that does to the QAM signal. Okay. And there you go. It's spreading around, and once it's done, you can see some eye closure. Again, the same sort of theme that we've had before, right? Okay. Um, so that'll be it for this demonstration. I am gonna sort of wrap that up here. I hope that you guys find it useful and that, especially for those of you uh, that are going to be working on lab number 3, please follow some of my recommendation. Either stop before we started talking about this, read the lab instructions, or if you already read the lab instructions, please come and see the video one more time. Um, I think it'll help you guys get through the lab and through all the different exercises in the lab. With no further ado, thank you for watching.